Hello, Christian.
Hey, Dr. Dish.
Hey,
Did you have a chance to see that recording yesterday or anytime?
both your links did not work. The main link, with the APS.
That's what I was worried about because I didn't know if you would have to have the same access as I did to that room. That's why I tried to get the recording, but the MP4 didn't work either.
Yeah, the MP4, it said maybe it has to do with something on my computer. It needed some codec. And so that's why I did not reply to you immediately. I thought I should try again using my home computer, but I never got a chance to do that. But it did not work on my office computer.
Okay.
So it is still, I haven't pursued it completely. That's the way to put it.
Okay.
But surely, you should try to show me on your computer, or I'll try to go through the link. So yeah,
Okay.
So that's why I didn't reply. You said you wanted to meet, but I couldn't go through that video.
That's okay.
But you were satisfied, right?
Yeah, I thought that it went fairly well. I added a little bit between, I added that reference slide, but for the most part, the presentation stayed the same. I did elaborate and give a couple more details in some spots where I thought I could use it after watching the practice talks on Friday. But I think it went overall pretty well. I had some positive feedback to it and a couple questions afterwards. So it seemed like it went okay.
Yeah, tell me about those questions later.
Okay.
Maybe we can meet tomorrow or sometime. Let's fix a time. Let's talk about that on the email. Okay.
Okay, sounds good.
Yeah. Meanwhile, I'll also go through the talk. Okay. So I posted a homework based on whatever dipole moment we constructed and a small string, like we are talking about an infinitely long string that has interesting consequences that we will talk about today. But if it's a finite string, it is significantly simpler. And one of the things is you have a circular loop in the problem and you have to do that. So I think it should be fine. I'll try to give some hints if necessary at the end of the lecture. So the first problem is very similar to what we did in the class, and the second problem is an extension of what we did in the last class, simpler version. Okay. This is meant to achieve. Change the view so that I can see you guys better. Yeah. Okay. This is, let's call this a, yeah, let me call this it's a little too heavy-sided topic, but let me call that. Basically, more mildly put, it's a Dirac string. Magnetic monopole has this feature that we have. It doesn't exist as of today, so why talk about it, right? That's a bit of it, but it's good to see what are the possibilities. What we did last time is, what is a Dirac string? It's a lot of point dipoles put one behind the other, right? So what is that? Point magnetic dipole. Dipole is simply M, which is a point basically, but it has a direction associated with it. So imagine, like we talk about a mass, right? Mass of a particle. The definition of a particle is just a point, but then let's associate a direction to it. That becomes a dipole moment. If you want to picturize this, think of this as a north pole and a south pole. So that's your south pole and a north pole. And then we say that in the limit when this, maybe another distance, so this has a magnetic moment is I times a square, right? So if you think of this as a loop of current and an area, so that's your area and that's your current. Take the current to infinity, and the area to 0. So that goes to 0, that goes to infinity. But you do this in such a way that this remains fixed, and that's your M. And once you do that, I doesn't have any meaning. There is no current in this point dipole. There is no area for this point dipole. The only thing you talk about is the quantity dipole moment, and that's the property. So it's a point object with a direction M. That's good. So then we said, let's talk about a Dirac string. So Dirac string is a lot of point dipoles aligned along a string. So that's a string. So there's a lot of, each point in here is a dipole, and we say that it is aligned with the string itself. So once you have a string, at each point you could have a magnetic moment that is not aligned with the tangent to the string. But if I were to align it with that, then that we will call as the Dirac string. So at each point now, I have a dm, or each element of the string that has a dm to that. And in particular, we will say magnetic moment per unit length. Now it is ds. So this is also a length s. That string is a length s. So this is equal to magnetic moment per unit length. And it's a vector quantity. And in general, this could be a function of the s itself. We call that in general. I don't say this is uniform or anything, like we define density, mass per unit volume. This is a magnetic moment per unit length, and it doesn't have to be uniform. It could be all distributed, more magnetic moment here, less there. All that is possible. That's a general definition of a Dirac string. What we did was a much simpler situation. We simply said it is along a straight line, just for simplicity in the analysis. We said that we started from the origin and went straight in this direction, and that was, let me say, This dashed lines represent that this is not a standard line. This is actually constructed out of a magnetic moment. If you want to think of it, so this has a direction associated with it, right? So that's your direction. So at the very bottom point, so there is a south pole and north pole, south pole, north pole, south pole, and so on. And we found the vector potential associated with it. And we showed that. So this is at the origin, right? So this is 0, 0, 0. And if I were to, and this goes to infinity all the way, and if I were to make an observation at some arbitrary point R, the vector potential, we'll talk about the magnetic field very soon, the vector potential associated with this at the point R is equal to, it is in the direction of phi hat. Phi hat, remember, if R is in this way, it's along a tangent to a circle around this axis. That's your phi hat. That's a cylindrical coordinate phi hat there. That's mu naught over 4 pi times this lambda shows up, and the cylindrical coordinate rho, which is basically rho is here, right? So that's your rho. And if I'm going to mix cylindrical and spherical soon, so this is going to be angle theta. Like that's your spherical coordinate angle theta. That's your cylindrical rho. This will be your z. Right? So that's your cylindrical coordinate z, rho, and that's your spherical coordinate r and theta. Phi will be in the xy plane, so you have to rotate it. So that's your z. That's your coordinate system. And we showed that the vector potential is equal to 1 plus cosine theta. Dependence comes in. So it's an angle dependent quantity. So if you're along the axis theta is equal to 0, then that's cosine theta is just 0. But if it is cosine theta is equal to 1, so that's 2. So when theta is equal to 90 degrees, it's 0, and then it becomes -1 as you go in the negative z-axis. So that is a angle dependence, and we will see what kind of angle dependence that is, or more than that, what does this lead to? So there's a very interesting feature that comes out of this. Let's go to purely spherical coordinates just for convenience, or not purely, I'll still keep the phi hat in there. So phi hat will stay cylindrical. In that sense, it's mixed. So this is mu naught over 4 pi. What is the rho? Rho in terms of r is, if this is angle theta, that's angle theta. So rho is r sine theta. Like in that right triangle, it is r sine theta. So let me write that as lambda over r. And the angle dependence is completely then in 1 over cosine theta over sine theta. Same expression, it's just I wrote it in 2 different ways. Okay. That's what we did last time. We are more interested in the magnetic field. Typically, we know that the vector potential has this feature that you can add or subtract some arbitrary function to that, which is called the gauge, and still the magnetic field does not change. So due to those reasons, we might wonder, how does this all dependence, is this really physical, or how much of this is physical, we can ask, right? So we just say that, okay, forget about the vector potential, let's go to magnetic field. So let's calculate the magnetic field then using del cross A. So let's calculate. Let's start with this expression, or before that, let me more explicitly write A of r is equal to 0 in the r hat direction. Maybe I made a wrong statement here. I said this is a mixed coordinate in the sense that phi hat here is cylindrical coordinate, and theta and r is spherical, but phi hat is common. Phi hat is there in both cylindrical and spherical. So this is purely in spherical coordinates. Phi hat, r, and theta, all three shows up. So I made a wrong statement there, but that's should not confuse too much. Right? So this is 0 r hat because there is no r hat component, plus 0 theta hat because there is no theta hat component in this, and this is having phi hat times that expression. That's just pointing out the fact that this is indeed solenoidal. That's what you say when it is in the direction of phi hat. A vector field is called solenoidal. It is basically looping around, right? It's circular. Okay, so that's vector potential. What is magnetic field? Magnetic field at the point R will be the curl of the vector potential. That's what we said, and this is given in terms of in general coordinates. If we know h1, h2, h3, so that's given in terms of h1, h2, h3. I'll tell you what h1, h2 is. I think we have used this before. So that's h1 times r hat, h2 times theta hat, h3 times phi hat, and derivative with respect to r, derivative with respect to theta, derivative with respect to phi. And here this is h1 times the r component, which is basically 0 in our case, h2 times the theta component, which is again 0, and h3 times the phi component. And in spherical coordinates, this h1, h2, and h3 is h1 is equal to 1, h2 is equal to r, and h3 is equal to r sine theta. Just to give you a picture of that, if you were to think of a spherical volume element, that's your r and that's your dr, right? And this could be angle theta here. So this is d theta. That means that's r d theta. That length r is what shows up as h2. That's one thing to realize. And next you have to make this three-dimensional, and I'll try. So that's your right. That's your three-dimensional volume, and that gave a height there, and this height there is basically r sine theta d phi. Okay. And that's because that circle has a component in there. So this piece of the circle has to have a component r sine theta. So you need to. So that's yeah. So how about a quiz, right? Quiz, motivate why this is r sine theta. Right? Show in a diagram why h3 is r sine theta. It also gives you the reason why the centripetal force acting in Carbondale actually is not the same as the centripetal force due to Earth's rotation acting on the equator. Right? It depends on the latitude. That's the same reason. It is. So if I were to, so if this was Earth, and that's your r, and if this was angle theta, this is r sine theta. Okay, is that visible? Oops, no. Okay. Same reasoning there, but is that clear? Any questions? Try to figure that out. look up spherical coordinates, but our reasoning is here to get this quantity. So h1, h2, h3 in our case is 1 over r squared sine theta. H1 is 1, so that's r hat. H2 is r theta hat, and H3 is r sine theta phi hat. You have partial derivative with r, partial derivative with theta, partial derivative with r phi. AR is 0 if theta is 0 and H3 is r sine theta. First multiply r sine theta and whatever we have calculated for that. So let me write that down. So that's mu naught over 4 pi times lambda times 1 plus cosine theta or 1 plus cosine theta divided by r sine theta. Notice the r sine theta cancels out. R sine theta cancels out, so it's a slight small simplification. Okay, so let's calculate this. Okay, so the magnetic field B at point R, right, is equal to take the curl, take the determinant, basically that's r squared sine theta. And first of all, h1, so that's h1 is 1, so it's r hat times the theta derivative, partial derivative with respect to theta of mu naught over 4 pi times lambda times 1 plus cosine theta. And the derivative of phi goes to 0, so that's not there. So that's one piece. What about the r theta term? So next is minus r times theta hat. So in the direction of theta hat, what are the contribution? There is a partial derivative of r with the phi component of a, but there is no r dependence in there left, right? Because r sine theta cancels out. There is no r dependence left, so that's 0. And phi derivative acts on 0 anyway, so that's 0 minus 0. No theta hat dependence in there. What about phi? Phi hat direction, both the components of a is 0, so that's not there either. Right? So plus r sine theta phi hat, and this is 0 minus 0. That's interesting. So because so there's only r hat components, but let's just evaluate this, right? This is easy to evaluate. Partial derivative of theta, so there is r hat, first of all. Then there is 1 over r squared sine theta, mu naught over 4 pi, and lambda. When I take the partial derivative with respect to 1, that gives me a 0. And I take a partial derivative with respect to cosine theta, it gives me a minus sine theta. I put a minus sign here, and then a sine theta. And the sine theta cancels again. So the angle dependence is all gone. Right? So this is equal to minus, let me write it in a certain way. That's minus mu naught over 4 pi lambda over r square and r hat. That's very closely similar to if I were to have a negative charge at the origin, I will have minus 1 over 4 pi epsilon naught times q over r square times r hat. So the similarity is no doubt there. It's just that you have to replace a q over epsilon with mu naught times lambda. And there is a negative sign there. And remember again, what is it, like if you want to give any analogy in here, there's a south pole, north pole, right? If an actual insightful thing is a magnetic moment is that, and you're putting this together right here like this. And similarly, if you are doing positive and negative charge, think of a dipole would be negative positive charge. That will be a negative positive charge. So there is a negative and positive charge, and so on. You can keep going. But one way to go do this negative positive charge is that, oh, you can say that these two cancel out. These are point charges, right? When you took this, an interpretation maybe is that these two get rid of each other, these two get rid of each other, neutralize. So you can cancel away everything and you're left out with a negative charge. Similarly, if you were to do here, north and south pole cancel, they're very, not a very obvious interpretation at all. But if you do that, right, you're canceling this piece out, everything if you leave, then there is a south pole left. And a south pole behaves like a negative charge. That's your south pole. This is the magnetic field due to a single south pole, apparently. Right? Is that really the case? Maybe. If that is the case, what should happen? Right? If this is the electric field due to a negative charge, how do we know that it is actually a negative charge? So we go to Gauss's law, right? It goes to Gauss's law, and what we say is that, oh, if there is an electric field, and remember again, this is magnetic field right now. Similarity is there. So you go to Gauss's law and say that, okay, what happens to the divergence of the electric field? Divergence of the electric field is not zero. There is a source here. So this comes out to be equal to minus q over epsilon naught. Right? That requires a proof. We have to use the divergence theorem, and we have done this few number of times. But to do this, what else comes here? If this is the divergence of the electric field, what is this right hand side equal to?
1 over r cubed.
No. No. If it is 1 over r, then it becomes 1 over r square. 1 over r square has this special feature. What's the divergence of an electric field? Point charge. What's the Maxwell equation?
Yeah, that was the charge density.
Yeah, that should give you the charge density, right? This is the charge, negative charge at the origin. What's the charge density for a negative charge at the origin?
Oh, is it a delta function?
It's a delta function, so there's just one delta function here. And it's at the origin. So this is charge density of a single negative charge at the origin. Hopefully that's visible. Is that readable? Is that really readable? Pin. How do I? Yeah, okay. But the mathematics is the same on the left hand side, right? If I were to do divergence of the magnetic field, like if you remember, this was a proof in the very first homework in this physics 320, right, in the first semester. So it's a non-trivial proof that if you were to actually take the derivative, it will go to 0. But then you use Gauss's law and say that I want to add up all these zeros and it comes out to be a finite number. So you say that, oh, it's a delta function. Similarly, the divergence of a magnetic field, if you were to actually calculate it, this will come out to be 0. If you naively calculate the derivative here, it will come out to be exactly 0. But if you carefully do this, like you do that for an electric field, this is equal to minus, right, this time mu naught times lambda, mu naught times lambda times the delta function. But Maxwell's equation tells us that del dot B is 0. Right? That's Maxwell's equation. It has to be 0. There is no, if Maxwell's equations are correct, that has to be 0. So, and we also know that that means there are no monopoles. This implies that this is a magnetic monopole, which is a south pole, right? Magnetic south pole. Right. Again, see the construction here. If, first of all, we are making it really point dipole. That's sort of relevant, but if you that's just for calculational ease. If you make this bigger and take it all the way to infinity, that's equivalent to having a magnetic monopole. Okay. And similarly, you can think about you can actually construct an opposite quantity. Let's say this is a straight line going down, and it's pointing towards the upward direction. That way you get a north pole on the top, right? If the arrow, if the dipole direction is pointing towards the point, then you get a magnetic dipole. How does it look like? So this is a string, right? So this is a string there, apparently a string of magnetic dipoles, but the magnetic field does not have any feeling for that string. That's just there. I mean, it's like an electric field to a pointer. In fact, even on that string, its magnetic field seems to be well defined. It's only at this point that you have a divergence, but this is not acting like a source at all. Like the string itself does not act like a source for the magnetic field. It's only the origin that acts like the magnetic field. Which seems to raise the question, is it really necessary that you actually go along the z-axis? And that can be actually verified, but it is harder to do that. So, I mean, you can do this using slightly more general formalism so that you don't have to go into the coordinate dependence of that. So in principle, you can have any string. So there is a point here. Go any string, and it actually just has to go to infinity as far as it is coming into the origin. That will have exactly the same magnetic field. It will be a point charge. With no field for this, remember, magnetic vector potential has this discontinuity in it if you want this source discontinuity. But the magnetic field has no field for that. Very non-trivial feature in that. Any questions on this? Questions or comments on this? Okay, so if not, so we have a few minutes left, and I said I will go over, at least give you hints on how to do the homework, right? So what the homework does is, it's very similar. So another example basically on a Dirc string. is that you have a circular wire, and this is the direction of the Dirc swing. This arrow, so this is constructed out of d m. So the radius of this is r. I think r, I don't remember what I used in the problem, and you have to calculate the vector potential for this. Remember that dm over ds is equal to lambda. And in this case, we can say lambda is the magnitude of this is uniform everywhere on this circle, but it's in the direction of phi hat. Right? So that's this is in the direction phi hat. And then starting from there, so this is uniform. Starting from there, you go for each element. What is dm? Dm is sorry, dA, right? What's a magnetic vector potential due to a single point charge? So that's dA is equal to mu naught over 4 pi times dm. That's the source crossed with. Typically it is r, but if you are not at the origin, so then you say this is r minus r prime. Let me just say r, right? No, but yeah, I think that's sufficient here. That's r, and this is r cubed. And you substitute that in there, so you get this is equal to mu naught over 4 pi. Oops. Mu naught over 4 pi dm is lambda times phi hat, so that is ds also shows up, right? So this is lambda times ds. So I had to integrate along this circle, and we have phi hat crossed with r, vector r divided by r cubed. And you have to, so notice along the circle, you have ds is equal to r times d phi. So you're basically going along. So if I were, so this, let me replace that also. So that's r times d phi. So the total vector potential will be equal to integral of dA over all the sources. That's equal to mu naught over 4 pi times lambda times r, integrate from 0 to pi. That's how you're integrating. And at that point, now you have to say this is phi hat crossed with vector r over r cubed. And you have to complete that integral. It gets much simpler depending on, because this is at an equal distance. From there, I will ask you to construct it. Remember, you're in undergraduate, you do a similar problem for current. This is not a current, this is actually a combination of magnetic moments, so slightly different, but the integration remains the same. Okay, and I'll let you guys work on that. Let me not give you more hints, but you can ask me if you want to. And I'll stop here. For a change, I'll stop early. At least I don't get to do this very often. Yeah. Any questions or comments? And from next time, we will switch over to either relativity or I want to talk about magnetic energy. Maybe it's kind of a good thing to talk about, but maybe I'll skip that and go to relativity directly. And then come to, once we have relativity in hand, then we will do actual dynamics, moving things. Okay, that's all.
See you later.
Yeah, bye, Jeremy.
Did you want me to just email you later and see if you could
Yeah, so let's see. Okay,